I'm a totally amazing person. I very strongly recommend all the students. The rest of us are jealous of you that you get to go to the coffee hour or whatever it's called, student hour, 2:30 to 3:30. He's not only a spectacular scientist, as I think everybody knows, he's also a remarkable person. He does things like take off a year to sail around the world or something of that order before starting graduate school. And then I'll tell it in its purest form. The way he got into MIT and started working with Ray Weiss was to climb over a barbed wire fence and knock on the window of Ray's lab, introduce himself and say he was interested in going to graduate school there. Yeah, this is, I mean, it's not quite as shocking as that. But anyway, it's wonderful to talk to him and learn so many wise things.
Yes.
And thank you.
Well, I don't know, you're far too kind, Dennis, but thank you.
Thank you so much for having you.
Okay, it's great to be here. Just it's such a nice size room. It's such a nice room.
Are you going to climb something?
Yeah. Right. Just interrupt as we go along. Okay, so and you'll see why this is. I hope this. Let's see. Can I? How do I advance here? That's not going. That doesn't go. I guess I can do this. Yes. So what do you see? Oh, good. Okay. So I want to tell you about an experiment we're calling PXS, and it's funded by the Simons Foundation, and it involves this cast of characters and a couple not shown here. This is Satarshi Chaudhary, who's a new faculty member, who's really the big driver here. This is a collaboration between Princeton Plasma Physics Lab, the magnet, JPL, for the amplifiers and Princeton, and this is Griffin, who's a postdoc at JPL, and Joel and Nate and Joe, and you'll see them later. They are grad students on it, and Roman Klebatov, who's a postdoc on it. Here's the team. So let me just give you a little bit of background, and this is probably such stuff that you all know by heart, but I will tell you anyway, and you can correct me. And then I'll tell you like experimental details, like what's going on, and that just may bore you because I think you're, I know you're a big theorist who are really interested in experiments, but I'll get a little more into the weeds than you might want to, than you might care about. We'll see. Okay, dark matter, and this then relates to that first slide, which is of course the anisotropy. Of course, there's overwhelming evidence, and everyone points to rotation curves as evidence for dark matter on the galactic scale. And I like to think about it as we know what it isn't. And it isn't, say, baryons. It's not stuff that easily interacts with light. It's not small planets. It's not black holes of the kind that we've seen so far. And of course, we want to figure it out. And it's everywhere on average a few protons per cubic meter in the universe. But the best evidence for it, I mean, so this is popular, the bullet cluster and those beautiful, beautiful images. But the high precision measurement of it is the third peak in the microwave background spectrum. Right? We know two things: that there had to be that we can measure the density to few percent accuracy, but also that it had to be there in the early universe, which is it's nothing recent. It had to be there well before 380,000 years. So it's actually a big bang. So there it is.
But some science popularizers say perhaps it's MOND. Are you saying it is a crackpot theory at this point?
I would never go crackpot, never say crack. I would say, so I think, so MOND's been tested on multiple scales. So it actually, slightly aside, right, using K as Z effect. This is the recent paper by Pato, Gallardo, and Spergel, and others. We can test MOND using galaxy clusters early on here. That's the largest angular scales, and we don't see any evidence of it. It looks like GR is fine. And then on the completely other scale, Scott Tremaine and colleagues were looking at the Oort cloud, and you can even test MOND on the Oort cloud. And in those two extremes, so hugely different length scales, there's no evidence of it in either place. So
Well,
I think it's go
you couldn't apply it to the third peak of the CMB anyway.
for MOND. Yeah, right, exactly. Yeah. No, yeah. Good. Okay. So CP problem. It's violated in the weak interactions. This is famously known, and there's not enough CP violation in weak interactions to explain the matter and antimatter asymmetry in the early universe. There's nothing in the standard model of particle physics. There's nothing that prevents CP violation in strong interactions. However, it's not been observed, and by looking at the dipole moment of the neutron, there are really strong constraints on the order of 10 to the minus 9, 10 to the minus 10 of what you might naturally expect from just standard, say standard by dot, from the standard model. So to explain that, Petchy and Quinn came up with a mechanism and that were turned into axions, as named by Wilczek, to explain this lack of observed CP violation in strong interactions. So completely different from cosmology. And so, and then that was realized, we'll get to that in a minute, as a great candidate for dark matter. So this is a slide from Satarshi, and it's divided in dark matter in roughly two camps. And I know there's many different kinds of dark matter and other theories to explain it, but this is just probably describes much of it. And on the right-hand side, right, are things like WIMPs, so small number density, de Broglie wavelength, much smaller than the detector, and you look for scattering, one would say xenon or argon or something like that. And on the other side, and so these are low occupation numbers, batteries out, but that's fine. These are low occupation numbers on the right. And on the left side, this is just to make up the dark matter, are large occupation numbers, so they have to be bosons. And the de Broglie wavelength is long. So if you have an axion that's about a micro EV, the de Broglie wavelength is a kilometer, right? So our experiments are all much smaller than that. And so we look for a coherent wave with a frequency set by the mass. So those are the two camps. And so, of course, we're talking about the one on the left, and the signature is a line. Right? We're looking for a line in the microwave regime. So we want to build an experiment to actually go see that. So here is the layout. Again, in particular, we're focusing on one part. I'll show you the landscape in a minute. Focusing on one part of the possible QCD Axion spectrum. And so this is, I just spoke about this, motivations, strong CP problem, dark matter candidate. There are a whole host of different kinds of axions, and we know they can exist over, I can summarize this, that they can exist over a huge mass scale. And I don't know that any particular one is depending on your theoretical background, is more motivated than the other, but the QCD axion has this really nice connection to particle physics. And so
but you say microwave because that's where you can measure.
And I will get, absolutely. So here's the full spectrum.
Sorry, maybe before you do that,
Yeah.
a line in what? Like a microwave line in what signal? Or
I'll show you that. I'll show you that in 1 minute. Okay. So here's a full spec. Actually, this isn't even the full spectrum because it goes off more to the right in mass of possible axion masses. And you can look on cosmological scales over here, or dwarf galaxy, I mean, super huge scales to constrain axion-like particles, so particles from axions from string theory and like. But in this, and so this is on the y-axis is the coupling constant of the axion to the photon. Show you a diagram in a minute, and axion mass on the x-axis. And then in this region are QCD axions as dark matter. And an experiment I'll keep coming back to or naming is the ADMX, which is really a pioneering experiment here in the method that we're using. And the method I should say that we're starting with was really done by was laid out by Pierre Sikivie. You know what that looks like. So here is our region. So and so here's the zeroing in on the yellow region. Here are two lines. So these two lines are two different QCD models based. So if the axion is there to solve QCD and it is the dark matter, it should be down to one of these two lines in this region. So that's the idea. If we can limit this coupling constant down to this line, we will have excluded or measured the QCD axion as the dark matter in this region. Okay. So these are proposed experiments, of course, except for ADMX, which is already excluded to this region, and Haystack is up there, and a couple of other experiments. And where we are looking, so here's you asked about the frequency, it's up there on the top axis. So the ADMX experiment excluded things down to a little above 2 micro eV as the mass of the axion. And we are looking from 0.8 to 2. So we're just looking in this small stretch here, but developing methods and technologies that can be expanded all the way down to much lower frequencies in the future. Lower masses, lower frequencies. So these are proposed experiments, but they're all using many, same microwave concepts, same related magnet technologies. You'll see that in a minute, and this is sort of a layout of the future. And to put it in perspective, so right here is about the gut scale. So this is, I think, maybe a broader way to think about this is a way to, probe physics directly in the lab at the gut scale. This scale experiment isn't quite the lab, but it's conceptually it's like that. Yeah.
So the colored regions are the sensitivity ranges of this experiment?
Proposed. Eventually.
Why do they stop at this line of dark? Don't they go below it?
Yeah, sure. They can go down anywhere, but you stop there just because that, what's the goal is to relate the QCD to the axion, to the dark matter.
But wouldn't it be interesting, even if it's not dark matter?
Totally.
Okay.
Totally. But that's, I think that, if to connect those two, you would stop integrating at there and then change frequency and then integrate more there, because it's not all at once. It's you go frequency by frequency, and how you do that is really subtle. So it's yeah. So those are just. This is I'm not to be. This is like staking a claim. My experiment is going to work in this region, right? And then develop what you need to do that. Okay, so we're just up in this region here, and one reason is we know how to do it, and that's there are a lot of microwave background techniques that we're bringing to bear on it, and it's the region after ADMX on the lower mass side where the prediction is the highest, right? So we can make hay as soon as possible. Okay, so that's the landscape. And then let me tell you about the experiment. And what you'll see is a little different than this, but I think this is, it was a beautiful paper by Kahn, Safdie, and Thaler in 2016. And this is just such a neat presentation of how to think about what axions do. So this is getting to your question, I hope. And so here's the idea. This was the abracadabra experiment. And actually, this is when I read this paper, I just thought, wow, that's an experiment you can do. So that's when my interest in doing these experiments started. So here's the idea, is that if you have a toroidal field, DC, that's the key. It's a DC toroidal field. And you're in an axion, you're nearby an axion, or they're everywhere, they're one here. The axion then interacts with that field. And the axion, I forgot to mention, it's a pseudoscalar, so it couples to the electromagnetic field differently than everything else you're used to. The coupling is such that it makes an AC current along the magnetic field. Right? So now you have a DC field in one way, and now you have an AC current along that field with a frequency that's proportional to the mass. Okay, so that's the connection between mass and frequency. So it makes an AC field along that, and then that AC field, and here, oscillating around here, then makes another B field that goes around it like this. And then here, this is such a nice geometry, you can put a sensing coil that is outside of the DC field, that's sitting in there, that's a squid, and it picks up the AC field, right? So then you've taken this dark matter candidate and you're looking for this AC field at that frequency, at microwave frequency. So conceptually, that's what's going on, and it's how do you implement that? And and I can tell you to give us sort of a sense. So for something like 10 to the minus 12 up there and around a micro EV, it is a few picoamps per square meter is J, is that current. So completely, you can measure picoamps, right? So if you get the right geometry, you can really imagine doing this. So, okay, so how do you do it? Oops.
Just a question.
Yeah.
So presumably this DC field is produced by some DC current wrapping around the torus. Does the axion coupling to that current, which might depend on the details?
There's a couple of it's the field. There might be some little coupling, but it's and there are people here who will tell you more. It's the Primakov effect. So it's the two photon coupling and so one of them is the DC field and the other is the microwave frequency. So it really and here, when people do these axion limits out in space, they're just like out around, say, pulsars or something, right? It's just to the field out there, and then you're looking for a mission.
Feel free to use the board. If drawing a picture would help you.
And is that
Yeah.
good enough? So are there any questions about that last slide? Because what we're doing is a little different, and you'll see how it is different.
What about sizes, right? Because your wavelength is like what, 30 centimeters or something?
Yeah. Okay. So
How big is this thing?
that sets the microwave cavity size, but the de Broglie wavelength of the
The Broglie, yes.
Okay.
I mean, the frequency of the resulting AC signal doesn't it depend on the size of your machine?
Yeah, absolutely. So we build a cavity, you'll see it in a minute,
Okay.
that resonates at a few hundred megahertz. You'll see in a minute.
Okay.
Yeah, totally though. You got it. Okay. So what are the building blocks of one of these? And you need, and I'll show you how it depends on these in a minute. You need a magnet, of course, because that's where the conversion happens. And the bigger, the better. So we are building a passively cooled superconducting magnet with PPPL, Princeton Plasma Physics Lab, about 0.8 Bohr, 5 Tesla. And you'll see how we're doing that. Then you need a microwave cavity for us that you put in that magnet in the middle. And that's where the conversion happens. So not the toroidal, we're doing a solenoid geometry. I'll get to that in a minute. So different than the toroid. And so put a microwave cavity in there, and to get the thermal noise down, it has to be cold. So we think we can get ours too. pretty easily under 100 millikelvin. We're shooting for 40 millikelvin. And then you need quantum limited amplifiers, right? Because these signals are small. So we're using these parametric amplifiers out of KPL. So it's just getting those three ingredients together. And so here's how we're doing it. So here is our cryostat. And we have a magnet here in the bottom. We'll blow this up in a minute. These are coolers to cool the magnet. We have a resonator cavity in the middle. And we've designed this thing, it's about 3 meters tall. We've designed this thing so we can parallelize the developments. The magnet happens in one way in the microwave cavity, and the readout happens on a different side of it. And so here is then a blow up of it. So here is, this is the magnet. These are the coolers for it. So these satellite coolers, and you'll see why this particular geometry is the way it is in a minute. Here's the area for the sensor. And right, unlike that toroidal geometry that had a really nice area that was field free, we're right above a solenoid, so you have to build in some bucking coils. So here we buck the DC field with another set of superconducting coils. And then on top is a dilution refrigerator, which cools the whole insert down. So this part, that orange part, is the cavity near 40 millikelvin.
Right, so where are the field lines going from this magnet?
Okay, 1 second. Okay, so good. So here's the field. And so this is the magnet, and the field lines, it's a little solenoid. Okay, so the field lines are going out like that, just like you did in pressure medium, right? So the field lines are going out like that. And here's roughly the contours for different field lines. And so this is now all modeled. And so one of the things that drives it is these are just the sort of details you worry about, right? Those guys do not work in magnetic fields this big. So you have to, you get them into as small a field as you can. But then you increase the cryogenic path, so you have to find that compromise, right? So it's that sort of thing we're working through right now. But we get releases from the company to share data and things like that. But anyway, that's the field line. So that's what it will look like. And we're in the process of developing this. I should also say these of that last two slides, I can sort of give you where the status is. So we're not quite to 2 years, and everything here you see is ordered, and you'll see some of the stuff that's being built.
Is just for orientation, is the magnet somehow groundbreaking, or is it pretty?
No one's made a conduction cooled magnet this big before. They're smaller, but this would be a new level. And
what does conductively cool mean?
there's no liquid helium. So now you go to most hospitals and you go to an MRI, right? There's some liquefier in the back, and the world is going to conduction cooled, which means you can cool them. Sorry for all the jargon, right? With a pulse tube cooler, which you plug into the wall, and an 8 kilowatt compressor, and through this very clever exchange of gas and a compression in a series of compressions and gases, you can cool helium to a few degrees Kelvin and extract watts of power. It's a beautiful advance. And so that's what we use to cool the magnet, for example. And that's what cools the dilution. ER equals dilution refrigerator, so it starts to cool a dilution refrigerator. And then you just use the dilution refrigerator helium-3, helium-4 cycle to get it down to 40 millikelvin. So it's, yeah. So yeah, I mean, so there are no liquids, these are starting, industry is starting to do this. But it's funny, one of the things we run into is they do not want to tell you how they do it because it's tricky. It's really tricky. And so sort of tell you, and then you read, and then anyway, we're working with, fortunately the team at PPPL they're figuring all this out and
Sorry, can I ask a naive question?
Yeah, yeah.
Because there are permanent magnets which are like few Tesla.
Yeah,
Why
permanent.
cannot I use that one?
Well, they're permanent. For one, so that would be, and on, this is, so 5 Tesla over this volume is enormous. So this is 6 megajoules of stored energy.
Oh, because this thing is big.
It's big
I see.
because
But
that-
tiny permanent magnets with few Tesla do exist. Right?
absolutely kitchen magnets get up to
Exactly,
half, right above a kitchen magnet. But now,
You
you know,
want bigger
B
size.
goes off like, it drops like R cubed, right? And so even if you peppered it with that, even if you did all the, rare earth elements, magnets, you couldn't do anything like this. So it's really, yeah, and plus, I mean, this is a big enough field that we cannot turn it on in the lab. We're getting a special place for it. This is a big enough field that you cannot shield it with a 10-inch thick piece of steel. That's how, I mean, this is a major field. So anyway, so here, so how do we do it? So here's then going back. So instead of a solenoid, instead of a toroid, the axion comes in, and now now here's our cavity. So this fits inside the magnet. The axion comes in, and now what we do instead of measuring that AC field, in the middle of the toroid, we are measuring the AC field in a microwave cavity. So everything is happening in that microwave cavity. And then we tune the resonant frequency of this by rotating an off-axis rod. And so if you rotate an off-axis rod, that changes the resonant frequency of the cavity. And so that changes the frequency.
So you have a metal cover above and below.
It's a cavity.
It is a
It's like a
cavity.
true E&M cavity. It is right out of Griffiths, right? And you go to Griffiths and you take those numbers and you put them in and you say, what's the frequency? And you get the right answer, right? Except almost, but you have to use materials and all that sort of thing. So here's the axion. So there are our cavities will have a Q of 10 to the 80,000 or something like that. I think our current one is 50,000 warm. And the axion has a width of about a part in 10 to the 6, just set by its kinetic energy. And so we're looking, so if there's one out there with one mass, it will have a line, something like that. And we have a resonance like that, and we're looking for that line in that. That's the signal. That's what it is. And the scan rate, if you will, so getting back to the scanning.
I'm sorry, what are the two lines here, delta nu C and delta nu A?
That's the resonant width of the cavity. Because it's
Your
got the
cavity
Q.
is
That
is not such high quality as
Yeah.
axion.
exactly.
Okay.
So the axion width, and so the axion width is set by its
Yeah.
distribution of kinetic
Yeah.
energy. So that's again part of 10 to the 6, and our cavity is based on, there's some great developments in cavity geometries, not so much in this frequency range, but we're trying to keep on top of them. So this is cavity to soup.
This is just the highest quality cavity you can make.
Yeah.
Okay.
Which is just based on the properties of stuff that you can put inside a magnet. So it has to be copper, basically. And that's going to be about 80,000, I think. Okay, so the scan rate, the frequency width you can go through per unit time to some limit is given by the quality of the cavity, because that's just the, so see it there, the width of that line. And here's the key thing: you want a volume, and it goes like B to the 4th. So you want a big volume, but you really want a big field. So you want a big field. That's a form factor that just tells you about the overlap of an axion signal with the magnetic field in the cavity, and that's just a scaling with temperature squared for the inverse temperature squared for the sensitivity of the amplifiers. So I think I've covered all that, right? We tune by changing it on resonance is where we're most sensitive, and yeah. Okay, we're building that, and actually here's Nate. So that's again that element. There it is. Our protocavity. We'll have to modify a little bit, but that even warm that already has a Q within a factor of a couple of what we should get and what we need, and we'll get that cold. But that's now, I think the cleaning rod just came out of the shop. Should have been today, should be today, actually. And so we're testing all that geometry right now. So that's that. Here's just the sorts of things you can see. So here's a simulation. This is probably a console. Yeah, you start doing these experiments, and it's to use all these software packages, and they're all slightly different. Blah blah blah. But this is what that's the E field in there, and then this is, we're not using quite this geometry. It'll be different, but we'll be moving this rod around like that, and as you change the rod, you change the resonant frequency, and the Q changes and things like that. And you can imagine the experimental challenges, right? This thing we're moving this thing, which is pretty big, at 40 millikelvin, and it's got to stay 40 millikelvin, and we've got to move it in a bunch of different positions. So we're working that out.
Sorry, I don't think I totally understand how you're moving the tuning rod around to change the resonance. I think there's some.
Yeah, it's like think of it as it's a if you're in the cavity, so a rod goes down through, it's just offset, and then this thing that excludes the field, because that's how you change the resonance, is just moves to the center of the cavity
I see.
and then off to the side through that motion.
Thanks.
And then-
It's the radial motion that's relevant,
Yeah.
not the azimuthal.
Yeah, but and it's right, because it's completely symmetric.
Yeah.
Okay. And then here, actually, the other thing we're doing, because we just got final approval of the purchase order this morning when I was sitting in 950 there, is we've actually have a separate development with another dilution refrigerator where we're testing all the amplifiers beforehand. So this is Joe Wiedemann, who's just developing all the electronics and testing all the electronics to make sure we can read out the cavity. Okay, so that's going. Here's another picture of that. We actually developed, again, it's doing experiments there are lots of challenges, right? So you need to have backups and things like that. So we have a series. So we test some things in a helium-3, helium-4 fridge that we developed for microwave background tests, and we've adopted it now to this frequency. Here it is. So we test some things in the helium-3, helium-4 fridge, which is good down to about 250, 300 millikelvin, and then pop them in the dilution refrigerator to test them all the way down to 50 millikelvin. And all this stuff is going on, and we're testing, figuring out what breaks and what doesn't. So this is one of the, it seems so low tech, but it turns out it's really not. So this is Joelle, and she's been working on the magnet. And so here's the challenge. So here's the magnet, this blue thing, this conductively cooled thing. And so that's a lot. It's 2.5 tons, more or less. It's 2.5 tons of copper and niobium tie. So niobium tie is going to be the conductor, and the copper is what is, helps stabilize it. And we don't quite know where we're going to end up, but we've set our plans. So now you've got to get 600 amps from room temperature down to 4 Kelvin. And one of the challenges there is that every joint has to be of order less than 1/10 of a micro ohm. Okay, that's small. You don't get that anywhere here in this one unless you solder something, right? And so, but you've got to limit the thermal conductivity as well, because you can't, it's 4 Kelvin. If you put copper down to there, you're toast, right? So all that has to be done with superconductors. And then there are different superconductors for different ranges. And so here, for example, so here we have separate systems out here to actually figure out how to feed in the current. And so we use a series of copper, and then you have to get the thermal balance right. BSCCO superconductor here, and then we transition here, either it will be to Rebco, the second different type of superconductor, to niobium ti, a third different type of superconductor. And so we're measuring that and figuring out how to make all those joints. And actually just a couple of days ago, figured out we could make all those joints. But then there are other just not silly, important experimental things like you can't solder two pieces of superconductor together and have them be superconductor unless the field is small, because you
How
see
come
the
you
field.
know about superconductors if you worked with CMB your entire life?
Yeah, this is what else I do. So we're figuring this out. It's really fun.
On your own, without help of professionals?
We're experimentalists. No, for real, yeah.
I am semi-serious. Are you really discovering all the superconductors technique on your own instead?
I don't know anyone who's done 600 amps down through Rebco yet, but so yeah, we're writing that up, and we're talking. People have done little bits of it, but this is a different thing. So, remember, the companies know how to. The companies have done this. But now we saw. It shouldn't be so flip, right? We saw. I think it's Sumitomo. We saw they did to niobium, a niobium titanium superconducting magnet.
So you will put them out of business by making
Yeah,
this public?
we'll actually publish it. So I don't know what they did. So, and Oxford, Oxford does this, but with different things. But I think actually no one's. So this is just. Let me see if it's on the next slide, and I'll tell you a sideline. Yeah, let's. So we were going to start with niobium 310 as our winding, and that's particularly good because it has a really high critical field, and PPPL had stocks of it. And this is to tell you where the field. So this is what's used in the magnets for ear. So that's why they have a bunch left over. We're going to take advantage of it. But that is, this is just, it's mind blowing. The way you do this is you wind a coil and then you bake it for a month at about, I think it's about 300 degrees. And that's what gets the niobium in the tin to meet. But then once you do that, it's ceramic. So it's no longer wire. So you have to design. So we're building one of these, a prototype. So then you have to do that. But now the way you have to connect that is you can't solder to it then. And you remember, and you can't do anything with it in the oven. So you have to, can't use any more. You can only use basically copper and stainless steel for the mantle. So then you have to, but it has been found out that Rebco, you can attach to it with Rebco. So, but Rebco is pretty difficult to work with. And so this Griffin has made Rebco joints in the past. And so we've been working with him, and it took us 3 tries before we could make a superconducting Rebco joint. So now we know we can do all that. So that was our breakthrough this past week for us. But I'm sure other people have done it, but commercial places aren't doing that. So
What
it's
does
just a
REPCO
side
stand for?
rare earth. Must be bismuth in there or something. I don't know. Something.
Barium copper oxide.
Yeah, there we go. There we go. Barium. Oh, good. Perfect. So anyway, so those are the things. Yeah, those are the things we're working on and figuring them out, and other people have. This is a huge industry, right? Other people have done this, but just not like this.
Andre's comment reminded me, don't you use superconducting bolometers in the CMB?
Yeah, but they're not big. Exactly. Right. That's actually a different superconducting effect. That's using 2 superconductors in a proximity effect to tune, but I won't talk about it later. So that in that case, we use actually the transition between superconductor and normal. For the CMB is how we make those sensors, or how NIST makes those sensors.
What are the commercial applications? Is that MRI or?
there we go. Eventually, I think eventually all magnets will be conductively cooled. Just because liquid helium is so costly and we're running out. So eventually they'll all be conductively cooled. So we're sort of in that path of industry is developing it and we're developing it and we'll see where it ends up.
But this still uses helium, just a lot less.
No, it's all closed cycle. There is no, I mean, it does use helium.
But it's closed.
It's closed, so it's finite. So it crudely, you can think of this as we've got our own little portable liquefier. That's not quite right, but roughly it's all closed cycle. So the trade-off is liquid helium for wall power. Yeah, so it's 8. This will be 8.4, 30 kilowatts of wall power to run. So, but that's it. So, there, we end there. So it's a blast to work on. It's just like it's new for a bunch of us. I think it's a great problem. We're grateful for the funding, of course. We have 3 more years, so we're pretty on some things we're ahead of schedule. On some things have been a little trickier. I mean, we just changed our final to what we're going to do for the final magnet. But we're, or stuff is ordered, it's designed. And we know what it costs and we know our, it's coming in, it's for great, right? So we're very close to our budget. And everyone's working hard and it's hopefully we'll get an answer and we'll see where it is and we had Pierre Sikivie was visiting the lab a couple months ago and he said, yeah, well, I think the Axion is just below where ADMX searched. So we feel like we've been blessed. That's all we need, right? So we'll see if that turns out to be the case. But we'll see. Let me stop there. Thank you. Anyway, sorry. Yeah, do I ask a question?
How long will it take to cover that range?
So we should be able to do it in if we hit all these other things. If we get our Q, you can see it's B to the 4th. So that B is huge, and that's unknown, but we seem to be on the right path. It'd just be a couple of months of integration, and then because that's what you plan on, right? Because if you plan on a year and you screw up by a factor of 2, it's 2 years. But if you design everything for a month and you screw up, you can wait a couple of months. So we're right around there. And it's all, anything like, I know this like from CMB world, like square root of cheese, just you want to get everything as soon as you can, because you just get old, right? You don't want to integrate forever.
So you have measured CMB, right? And now you will spend 5 years of your life and you will measure nothing with probability 99.95%.
Unless.
And that's being generous.
Sikivie.
Right. So I have 2 questions about this. One thing is, in all likelihood, of course, you will get nothing. You realize this yourself.
Yeah.
So, question: this development of these techniques and whatever, not by private but by science, is it gonna do something for the world, something good or not?
Yeah, well, I said the magnets are huge.
No, but I mean the fact that you make this technique public now, is it something which will be of interest in other applications or whatever? How do you justify getting 0 in 5 years?
Okay. How do I justify it?
For yourself.
I should say just
No, I mean for yourself, not for the funding.
Okay, so just some context. So we're actually, and I'll tell you a little bit about this afternoon, right? We're working on a B mode experiment. So there, everyone has their own prior, right? That might be 0 too. So we feel very much in the spirit of Bob Dickey, right? You spend your life measuring things that might well be 0, and it's not a bad thing to do because you learn so much about nature along the way. But getting back to this, so why, like, what is?
Why do you do it?
Why, yeah, so the other element, and I breezed through this pretty quickly, and you should really get Satoshi up here to talk about it, is the core, the way this field is going to move forward, and we'll take advantage of this too, is using squeezing techniques for microwave photons, microwave radiation. And so everything we plan for here, you can get by with amplifiers working at near their standard quantum limit. But to go beyond that, you need to go into these squeeze states, say like LIGO is the best example of this, right? You're taking, if you think of the noise, and think of Heisenberg in X and P, or think of it in it's going to be X and P is the conjugates in photons is going to be.
I mean, going beyond quantum limit.
Yeah.
So.
And what you want to do is you want to squeeze in one of those, say delta X, and so you can measure position in that case better and better and better. And there's a complete analog here for measuring the noise in a microwave cavity. And the haystack experiment has done this. So the limit they set on it's I should have mentioned them beautiful. I'd say for us, ADMX is one pioneering experiment, haystack is the other, is to actually set their limit that they do on the presence of the axion. They use squeeze states of electromagnetic radiation. It's in a different regime than we are, but this is a whole new frontier in measurement and measuring electromagnetic radiation. And so experimentally, that's the other thing that really, excites me. It really is the core technique that will, if we can figure it out, right, it'll be around in lots of contexts. And I think, you read about it in condensed matter context. But squeezing is really subtle. It depends on, because the vacuum is different in different regimes. Or if that's a big part of
and your measurement will require
ours will not to get to that limit will not. Those big ones, they're staking out the claim, the gut scale, will need to squeeze at factors of improving or reducing the noise by 10 to 20. Whereas LIGO, I think, is down around squeezing it maybe 6 dB now, something like that. Not much, but they're getting there, right? So this is in terms of what it means to measure nature better and better. This will be necessary element of that in the future. Fundamentally, how well can you know nature? Yeah.
Maybe a related question. You said in the beginning that what you're doing could be scaled to lower frequencies, lower masses. So if you don't have to do the squeezing, like what parts exactly are scalable?
So good. So to get, let me go back here. So it gets tougher. It gets so we're up here, and you guys are like keen into all the challenges like, oh, it's great. So on the upper half of this band, we can use just straight Sikivie's idea of a holoscope, which is just a big magnetic field in a resonant cavity, and looking looking for a line. As the frequency gets lower and the wavelengths get longer, you move from that resonant structure to more of a lumped element structure. So instead of, if you remember the toroid picture from the abracadabra experiment, that really was a lumped element. Like you would couple outside of the magnetic field with physical elements to measure the resonant frequency. So you really you change there. The change happens at the bottom of our band. More like it's sort of right through there, where you start to move from a straight cavity holoscope type thing to a more lumped element. So have been modeling in the lower part of the band. We need different coupling techniques that we're working on. So we go, and those changed all the way down. So we're starting to learn those techniques. So that's one element that scales. This is, so I should say, so of that group I showed you, everyone else is part of DM radio cubic meter. I'm not, but those guys are. Where they're really going much, have much more of this in the long wavelength limit. And so, and there's a lot of, you can imagine a lot of communication for everything on that. Just silly, just not silly, I shouldn't call it silly because it's hard. It's cryogenics, just how do you do this cryogenically? How do you read out these signals? The amplifiers will be similar for upper part of the band versus lower. Going to here, you need a huge magnetic field, and that magnetic field is so big that you're getting beyond the critical field of NIMTI. And so this will probably require niobium-310. It's the best material now, that one I told you about that gets heated up to some high temperature. So this is why we're building the monocoil. So this will require that sort of magnetic field. So we're part of what we're in our test coil, we're figuring out things that will be important for that. And I should say at the same time, this is Subtarshi and Roman are building, because there's side experiments across this whole region, building a resonator, which is a lumped element for, is it up here, date for this experiment, EM radio 50 liter. So they're building the resonator for that, which is a bunch of related, how to make superconducting joints that last through thermal cycles, all that sort of thing that aren't soldered. So they're building that. So there's a strong connection across the board. And I should say this is a connection to the haystack guys. We're just up at Yale and just trading techniques. I don't know if that quite answers your question, but there's a lot of commonality, and a lot of it is just how do you think about all the problems, because they're challenging. So it's a little wishy-washy, but there's some very technical hard points on there: magnets, amplifier squeezing technology, and even resonators, just looking at the resonators.
That was just wonderful.
Oh, thanks.
Thank you so
That's
much.
my pleasure.